visible? It's visible. All right. Okay, good. Okay, so last time we covered Newton's laws of motion, right? We were talking about Newton's laws of motion, Newton's first law of motion, which was telling you more about the inertial frame of reference. Then we talked about second law of motion, and Newton's second law of motion was related to the unbalanced forces, right? Then we talked about Newton's third law of motion, and Newton's third law of motion is very obvious, and even despite the fact that it's obvious, it still causes some problems in people, and it appears at first as though if it's all wrong and everything seems counterintuitive, but the point that you have to remember is that the forces act in pair and they always act on different bodies, right? So that's what we learned last time. So what I'll do now is I'll quickly recall all of the things that we have covered in the topic of forces, except for this thing. Never mind. We'll start with this thing that the first thing is balanced forces, really, which is Newton's first law of motion, right? So Newton's first law of motion, and we saw that it's related to balanced forces. And how is it related to balanced forces? We know that if a force is balanced, so if a force is balanced, what does that mean? Can anyone tell me? What does it mean if I say a force is balanced?
One force is equal to the other force.
Right, exactly, right. So if the sum of all the forces mathematically, that would mean that sum of all the forces vanishes, right? Or it's equal to 0. So there is no resultant force acting on the system. All right, good. So then so for balanced forces implies sum of all forces is 0. In simple English, that's just saying that the resultant force on my system is 0. So there is no resultant force. If there is no resultant force on the system, what would that mean in terms of motion? Can anyone tell me?
It would be
object will stay in a constant motion, sir, at a constant speed, sir.
All right, that's exactly. So it will not be accelerating. There will be constant speed or constant velocity. So that's just implying that the acceleration of the entire system would also be 0. If the acceleration of the system is 0, what does that tell you about motion? I mean, you already gave me an answer. That would mean that the object will remain in motion in constant velocity, right? But there would be two conclusions from this thing, right? One is constant velocity. The other one is, anyone?
constant speed.
But that thing is covered in this thing, constant speed or constant velocity. What could be the other conclusion if I just tell you that the system is not accelerating? There are two things that you can conclude from this statement, right? One, some of you may say that it has constant velocity or speed. That's correct. What could be the other possibility?
All the forces
The other possibility
equals
could
to
be that
0.
the system is, yeah, that's something that we are coming from that, right? So we are coming from sum of all the forces 0, acceleration is 0. Acceleration 0 would imply that the system is at constant velocity or speed, or it is at rest, right? So even when the system is at rest, at that time the acceleration is also 0, and the acceleration is also 0 when the speed is constant, right? So if I tell you that the system's acceleration is 0, you will not be able to reach to a final conclusion single statement. You cannot just say that its speed is constant or that it's just at rest. You will have these two informations, and then to conclude from these two informations, you would need to know about the velocity of the system, right? So this thing is telling you that the velocity is 0, and this thing is telling you that the velocity is constant. Any number, right? So it would just be a number, which would not be changing with time. All right. So is this thing clear? This is more or less
Yes.
Newton's first law of
Yes,
motion
sir.
as well. Okay, good. Okay, so the second thing that we talked about is Newton's second law of motion, obviously. Newton's second law. And the second law is more or less closely telling you about unbalanced forces, right? Because in unbalanced forces, what does that mean? Unbalanced force implies
The two forces are not equal.
they're not equal,
The
right? So that would essentially mean that there is a resultant force acting on the system, right?
Yes.
So when you add all the forces, it would not give you 0, right? Okay, so this would mean that the sum of all the forces on the system is not equal to 0, right? It is any constant positive number, right? Okay, so then this would imply that there is some net acceleration on the system. So acceleration is also not 0. And of course, if the acceleration is not 0, if I tell you that, then again, you can make two conclusions from this thing. You can say that the system starts moving, the system starts its motion, right? And the other conclusion that you can come to from this thing is what? That the system
Is already started.
observes a change in velocity, right? So yeah, so the system observes a change in velocity. Observes change in velocity with respect to time, right? So the velocity changes. When I say velocity changes, I'm using the word velocity. So it should be very clear to you that I also am talking about direction, right? So even if there is a change in direction, that would mean that there was a non-zero acceleration. And that acceleration is known as the centripetal acceleration, or the acceleration responsible to move the object in a circle. But so is that clear as well? Newton's first law and second law.
Yes, clear,
Right?
clear.
All right. So mathematically, then I can write down the Newton's second law as sum of all the forces is equal to mass of the entire system, right? So and the acceleration of the system. I use this index I, meaning that suppose that I have a system. Suppose that this is a system. It's composed of, one way to think about this is it is composed of atoms, molecules, or suppose there are so many balls contained inside a box, right? So every ball would have its mass m. So suppose this ball is m1, this is m2, this is m3, m4, and so on, right? So now if I accelerate or apply a force to the system, in practice, all of these masses would experience slightly different accelerations. So this one way to think about this is in terms of multiple masses and multiple, those masses experience multiple accelerations. Right. So that's Newton's second law of motion, mathematics. All right. So you can say that for any object which has a constant mass, suppose that I have a ball. The mass of this ball is going to be a constant, right? You don't see a mass changing masses, right, of a system. It's constant, and then if you take the product of this mass and suppose it accelerates, then that would give you F equals ma. So I'm just telling you what you already know. This the point to be noted here is that this force is the resultant force, right? It is the resultant force.
Or the unbalanced force.
Or the unbalanced force, exactly, right? So yeah. Now suppose I tell you that this resultant force F, let's just write it Fr as resultant, is equal to 1 newtons, right? Suppose I have a system, I have this ball of mass m, and I say that the resultant force on this ball is of 1 newton. 1 newton of resultant force acts on this ball. What does that tell you about the physics?
That it's
What is happening?
that 1 Newton of force is acting on the ball.
1 newtons of force is acting on the ball. What that would mean is, suppose the mass of the ball is 1 kilograms. That would mean that a 1 newton of force would be responsible to accelerate this 1 kilograms by 1 meters per second squared. Now, again, you can ask, what does that mean? That is telling you that after every second on the clock that passes, so these are seconds, right? These are seconds. After every second, it would gain a velocity of 1 meters per second. So at 1 second, it would be 1 meters per second. This is the speed, right? And let's say this is the time. After 2 seconds, it would become 2 meters per second, then 3 meters per second. So the velocity is increasing, right? So it's accelerating. The difference between these two velocities is always 1 meters per second, 1 meters per second. So every second that passes, the velocity increases by 1 meters per second. That's what the force
Yes,
of 1 Newton.
teacher. Is this in a vacuum? Because a vacuum of space, as in on the ground, it could not. It can, the frictional force will increase as well.
Yeah, your conclusion is absolutely right. But the point that I was stressing on was resultant force, right? So the
Yes.
resultant force, meaning then if the resultant force is 1 Newton, we are already including all the frictions and everything. So maybe the force acting forward was, suppose that it was 2 Newtons, and we have already subtracted the 1 Newton of friction, which would have given you a resultant force of 1 Newton, right? So this is the force that I'm talking about over here, right?
Yes.
Okay, good. Okay. And so this is Newton's second law, right? Now, let's finally end this discussion of the summary by Newton's third law. And we all know that Newton's third law of motion is telling you that wherever there is some action happening, there happens an equal but opposite reaction, right? Which would mean that suppose that I have this ground and I place a block on this ground, right? So this is a block. Suppose its mass is 2 kilograms. Then because of suppose that the ground is the surface of the earth, then because the earth has this acceleration due to gravity as let's just use 10 meters per second squared. That would mean that the weight of this block, weight is a force, right? It is, and it acts towards the center of the earth. So it's the weight of the block, or this force, is obviously 20 kilograms, just m times the acceleration due to gravity. This would mean that if there is this force acting, I used 20 kilograms. I'm sorry for that. I meant 20 newtons, right? So this would mean that there is an equal but opposite force which acts exactly opposite to this vector, which is this vector, and this is the normal force. Now, you have to remember that this force which is acting downwards, which is the weight, it is the force due to this block. And this normal force N is due to the ground. So these are two different bodies. One is the block and one is the surface of the earth. So this force is due to earth and the weight is due to the block. So is that clear?
Yes.
Right. Okay, so that is the most important point that you have to remember in Newton's third law, that these forces act on different bodies. If you remember this one point, you will never be confused with Newton's third law. All right, so now having revised all of this, let's do a problem, right? And let's practice all the conceptual things. Suppose that you have a container, a block or a container, whatever, and suppose it's a very heavy block, right? So let's say that its mass is 1,000 kilograms, and this container is stationary. It is just resting on some surface, and suppose that there is no friction. So this is a frictionless surface. That would mean that if I move the block on this surface, then there would be no friction that would act on this block, right? Okay, so suppose I attach a string to this side like this, and I apply a force and pull this string to the right, right? So suppose the string is very small and tiny, so it has no mass or anything. And suppose I pull the block to the right, and suppose that the block moves to the right with some speed, right? And suppose that speed is 20 meters per second. And it gains this speed of 20 meters per second in 5 seconds, or you can say that it moves to the right in 5 seconds. Its speeds become 20 meters per second. So what you have done is, obviously, you have applied a force to the right, which has produced an acceleration in the velocity, and the velocity increased from 0 meters per second to 20 meters per second. And this increase in speed took a total time of 5 seconds. We are required to, first of all, at least compute this force, right? So when I say that the block is sitting or it's resting on this frictionless surface, that tells you that the initial speed of the block is
0.
0, right? 0 meters per second, because it's sitting still, minding its own business. The speed is 0 meters per second. Of course, we can go into details and we can argue that it is not really 0 meters per second. It could be something else as well, depending on the observer. But now I'm just getting ahead of myself. It's 0 meters per second, right? So I was just telling you that there is no absolute speed, but relative speed is still 0 meters per second. And the final speed is obviously 20 meters per second. And the time it takes to go from 0 to 20 is 5 seconds. What can I do with this information? Can I compute the acceleration of
I
the
think
system?
yes.
Right? Yeah. So let's write down the expression and see if I can. So I know acceleration is the change in velocity, right? Let me write it like this: change in velocity divided by the time it takes to change that velocity. And I can write this as v minus u divided by the time it takes to gain or change that speed. of course, I know already I have V, I have U, and I have T. So I'll just put in these X values. So V is 20 meters per second, U is 0 meters per second, and the time it takes to cause this change in the speed is 5 seconds, right? 5 seconds. So that gives you 20 meters per second divided by 5 seconds, which gives you 5 fours are 20, and this becomes 4 meters per second per second. That means that, what does that mean? Can anyone tell me? Of course,
That's
doing the math, yeah, doing the math is very simple, but understanding what it means is what we want to know, right? So yeah,
It means
what does it mean?
that every second the speed increases by 4 meters per second.
square.
Right, exactly. So as every second that passes, the speed increases from 0 to 4 meters per second. So again, if I write it as I can write it like this, right? So 1 second passed, speed increased to 4 meters per second. 2 seconds passed, speed increased to 8 meters per second, right? 3 seconds passed, it increased to 12 meters per second. 4 seconds passed, it increased to 16 meters per second. And 5 seconds, it increased to 20 meters per second, right? So add 4 to this and you get 20. So you can see that, of course, we are in line with the statement of the question, which said that it takes 5 seconds to go from 0 to 20 meters per second. All right, so we have now we have acceleration of the system, which is 4 meters per second per second. So the question was to compute this force. How do I compute this force? This one.
You have
So
now you need you have the mass of the object and you have the acceleration. Now you multiply them.
Multiply them, right? So you write that sum of the forces is equal to mass times the acceleration, and mass of this object is 1,000 kilograms. Acceleration we found out to be 4 meters per second, and this gives you 4,000. You can write it as kilograms meter per second squared or just newtons, right? It's a force. All right, so the math is done. The math is simple. It is telling you that the force F is equal to 4,000 newtons. Can someone tell me what does that mean physically? Or now can someone explain this entire situation physically?
The person pulled the string for 5 seconds with the force of 4,000 newtons with the acceleration of 4 meters per second square.
All right, so more or less that's exactly what happens, right? So yeah, so that's what happens, right? So you pull when I pulled the string, I applied a force of 4,000 newtons, and that 4,000 newtons of force was responsible to produce an acceleration and to move this block. And that 4,000 newtons was strong enough to increase the speed from 0 to 20 meters per second within 5 seconds. So if I had keep on pulling this object with this force, as every second would pass, the speed would increase by 4 meters per second. So, all right. So let's, yeah, sure. You have a question?
so yes. So
Yes, please ask.
how does the Newton's third law uh, come in this problem, sir? Like where is the equally opposite reaction happening, sir? In the example you
Oh,
given.
doing this problem, we did not talk about Newton's third law. We were focused on mainly the Newton's second law of motion, right?
Yes,
But
sir.
if you still want to know, our goal was not to understand Newton's third law from this problem. It was to understand really the Newton's second law, which you will find
Yes, sir.
more mathematics is involved in Newton's second law of motion. Uh,
Yes, sir.
you can still talk about third law of motion in multiple ways. One of the ways is that this object is sitting on this ground, so it has a weight, and there would be a normal force. Third, and the so if for the force that is acting towards the right, there then because you're pulling it to the right, still you know that there would be some friction. If this surface was not frictionless, then there would be some friction which would be to this left side, right? If the surface was not frictionless, in that case, friction itself is something that you will not study at this point, but it's equal to some coefficient, and this coefficient is called mu, or it's also known as the static or dynamic coefficient of friction. And then you multiply it with the normal force, which is this one. This tells you about the frictional force. And then you can also talk about Newton's third law, because then this friction force is, because it's related to the normal force from the ground, then this is also related to Newton's third law of motion. But that was not the goal of the problem, right? So I'll just get rid of this thing, because you're not required to understand this F equals mu times n thing at this point. So is that okay?
It's clear.
All right, so we have less time remaining in the meeting, and I mean, it's not too less anyways. We still have 8 minutes, really 9 minutes. We'll talk about free body diagrams now. And that's the last thing that we'll be talking about in this topic. Uh, by topic, I mean forces in general. The next thing we'll be talking about is slightly mass, weight, and density. Mass, weight, and density, we have talked about those things in the physical quantities topic chapter when we did physical quantities. So we'll quickly go through mass, weight, and density, and then we'll come to the turning effect of forces, which is a rather more interesting topic, where we'll also be talking about torques and the conditions for equilibrium. Those are very interesting things. Okay, so yeah, now let's talk about free body diagrams. Do you have any idea what do we mean by free body diagrams?
No, I don't think so.
Okay, so for example, this thing that we drew over here, this one, or
Yes.
this one. If I say that this is a free body diagram, would you have any objection? I mean, that's a very stupid question to ask. I'll just say that these diagrams are what are called free body diagrams. Now, let me see if we drew any more. For example, even this one, this ball that we drew over here, it's also a free body diagram. What it means is that we can draw very simple diagrams. You don't have to be an artist to make these diagrams. Just draw anything. For example, suppose that you have a person, right? So maybe you can draw something like this, and suppose that you want to say that its weight is like this, mg. Then you could have drew this diagram, and then even if you go more further and you say he's standing on the ground, then you could just draw this line, and you can say that the ground exerts a force back on the person, and the person exerts the force mg on the ground. This is a free body diagram. You can have multiple forms of free body diagrams. It doesn't even matter if you drew this person like this. I could have simply made a ground with a line and a point on this ground and say that this point is a person, and then say that this person's weight is like this mg, and then the normal force from the ground on the person is this n. These two are exactly the same thing. They're equivalent, right? Now, before we move further, I wanted to tell you about some of the geometry, but I mean, it's not really required. You're not really required to know that, but it's interesting to know some of the things. For example, when we say we draw a point, right? What do we mean by a point? Can anyone tell me what is a point? How do you define a point? We have been using points so many times. Can you define what a point is?
A point is like a description, a simple description.
It is a
I
definition
mean,
of two-dimensional plane.
okay. Any
Simple
other
definition,
ideas?
which has no dimensions.
Which has no, did you say no dimensions,
No, not,
dimensionless?
yes, sir, dimensionless.
No dimensions, right? Okay, yeah, so
Yes,
that's a more technical answer. So a point is something that does not exist, but it exists, right? So it's something that does not exist, but it exists. It's a philosophical kind of way to think about it, because, for example, suppose that I draw a point. This is a point, right? It's a very thick point, but it's a point. I can decrease the size of this point. Let's do that by this thing. Suppose I say, okay, we have decreased it. It's still a point. I can do this thing. I can keep on decreasing. So I decreased it again. Still a point. I'll take this and I'll decrease it more. It's almost gone, but if you look closely, here you will still see a point. There's a point. You can keep on decreasing the size, decrease it to as much as you can, and it will still be a point. So really it has no dimensions, and then you can say that it does not even exist. But suppose I have this point, and suppose I have another one, right? This one. How, let's say it's here. How can I differentiate between these 2 points? Suppose I take this point as well, and I keep on decreasing it, right? So I decrease it, and I keep on decreasing it and decreasing it. So if I said that this point, it really does not exist, and if even this thing does not exist, then how do I differentiate between 2 things which do not exist? I can
You give them
differentiate.
names. You can give them names, I think. Point A, point B.
Yeah, and those names would be depending on their position, really. So where do I have this point and where do I have this point? So that's one way that you can differentiate between the 2 points. All right, now points do not exist. That's something that I have told you so far. What is a line then? In
The
mathematics,
ground.
how can I
The ground.
yeah, but mathematically, how do I define the geometry of this line? How can I make a line? The smallest
all
constituent
sets
I
of,
have is a point, right? So I can use point to make line,
Yes, point,
right?
point, point. Yes.
yes, sir, a line is all the sets of points um going
You can say
in both
composed or
the
joined together.
direction infinitely.
Yeah,
Yes, sir.
yeah, exactly, right?
From two
So
points through which goes through 2 points.
Lots of points, really. Yeah,
Yes.
you can also say that suppose I have a 1 over here and 1 over here, and infinitely many points can sit in between these 2 points. Suppose this is point 1 and this is point 2. Infinitely many points are sitting in between these 2 points, very close together, and that's what forms a line. But the philosophically interesting thing is, if I said that points do not exist, then a line does not really exist as well. And that's very true, by the way, because in reality, in your practical life, you'll never see something that is a point. You'll never see a point. You will never even see a line, a one-dimensional line. In your real world, three-dimensional spatial world, you can never see a line.